Last week we started talking about Kalman filter. There are a few things I want everyone, okay, to remember. It's not formula, it's just the conceptual ideas. You have to remember a few things. First of all, we didn't introduce Kalman filter yet, okay, but I gave you a preview of Kalman filter. You should know it does exactly the same thing as Lundberg observer. Okay, Kalman filter does exactly the same thing. If you represent it as a block, the input output are exactly the same. The only difference is the modeling assumption. The plant is also the same, okay? You don't change the plant. It's just your model. When you design the observer, when you design the state estimator, the model in your mind is different. Kalman filter assumes a stochastic model which incorporates uncertainty in a more formal way. Lundberg observer does assume a linear deterministic model. Okay, so you should remember Kalman filter does the same thing in terms of functionality, does the same thing as Lundberg observer. Okay, that's the first thing I want you to remember. Second thing I want you to remember at this stage, later on you will realize why is the case. Kalman filter is nothing but I will ask you to maybe write this down in the final exam maybe, okay? It's nothing but a recursive way to compute conditional expectation. Let me repeat. You have to remember this. This is fundamental nature of the filter. It's nothing, mathematically, it's nothing but computing a conditional expectation. That make everything simple. Okay, now we only need to answer two things, right? Why Kalman filter is a conditional expectation and how to compute it. I tell you the answer already, okay? You should have this question mark when you are following me throughout the lecture, okay? So have this question mark, why Kalman filter? And how should we compute this? Okay, to truly understand this, I think your prior training in probability is not enough, so we go over very, very fundamental stuff in probability, but the objective is clear. I want you to understand conditional expectation, okay? In order to understand conditional expectation, you have to understand conditional probability. So that's our story. You see the logical steps, okay? So we need you to conceptually understand everything because the formula is very simple. I can give you the formula and you'll be able to use it for sure, but you don't understand, that won't help, okay? So you have to understand. All I'm trying to do is trying to make sure at least 80% of you, not because of who has a strong background, it's just because 80% you may spend a lot of time on this, okay? If you decide to spend time in class and after class to practice, I want to make sure everyone understand the derivation of Kalman filter. It's very challenging, okay? But I've done this before, I think you will be able to do it. But you have to be patient. We have to go through the basics, okay? So last time we started reviewing probability and conditional probability. Two things I want you to remember. First of all, probability, whenever I talk about probability, I implicitly assume three things. What are they? Sampling space, event space, and probability measure. Sampling space is a set of all the possible outcomes, and the event space is the subset of all the possible subset of these outcomes. And the probability is a measure, maps the likelihood. So give a metric to the likelihood a particular event happens. Okay, so again, I want you to know that probability is your knowledge, okay, your personal knowledge. Your knowledge will be different from mine, by the way, okay? I have a different probability model in my mind, okay? So it's everyone's belief, okay, about certain things. But what we are teaching you is that how to formally really express your knowledge about uncertainties. As I mentioned, I think that may help some people, okay? But that's my personal view, okay? The world is deterministic, as I mentioned last time. Okay, if you toss a die, 扔个骰子, okay? The number show up is 1, 2, 3, 4, 5, 6 is determined. The reason is probabilistic is because you don't know it. It's lack of information causing uncertainty. Everything, I think, is deterministic to a certain level. It's just too many details out there. You wouldn't be able to get access to those information, so you have to guess. Okay, you want to guess means you don't have enough information to fully determine the uncertainty event. Okay, so that's really depends on your knowledge about certain uncertainty. That's your information. Okay, when you make the decision. Another thing is that I want you to have a good understanding of conditional probability. Do you remember? I think you should remember this figure. I think that will be helpful, at least help me. I didn't see this figure, but that's how I think through the definitions, okay? What is conditional probability? The key word here is not conditional. The conditional probability is, at the very bottom, it's a probability. It has its own sampling space, has its own event space, has its own probability measure. Okay, you eventually, formally, you can write them down. Okay, omega tilde, f tilde, p tilde, but that would take too much effort. So all the probability this formula gives you is nothing, but you can continue to use your original space, an original probability measure p, to define the new probability. Okay, so what this means is the probability of an event A after B has occurred, right? When B occurred, B becomes the whole sampling space. We explained this last time. Okay, the key is that conditional probability is probability. Okay, the definition is just link this probability definition to the original definition of probability space. Okay. Then to specify probability, we need what? Probability mass function or probability density function. Then we can compute the probability by summing over or integrate over the outcomes that lies in the event you are trying to compute the probability for. Okay, then we somehow jump to random variable and random vector. I want to assure or maybe emphasize again, in this class and in any class, maybe not in other class, sorry. In this class, number, scalar, and vector and matrix, they are the same. Okay, mathematically, they are just a quote-unquote number. It's just depending on the number, it's in the real line or in R2 or in R3. You can think about a dot, a point in the line, on the line or on the plane or in the space. It doesn't really matter fundamentally. So we don't distinguish vector with scalar because that will make the notation really hard. Some people will see X, there's an arrow above it, right? Or arrow below it. That kind of notation is very heavy. Again, okay, this part is, I want everyone to be able to kind of speak out with me, all right? What is deterministic? And what is random? What's the difference between determinist and a random variable? I can have a variable that is deterministic, okay? So you should be able to speak this out in English. That will help you understanding. Deterministic is a single valued variable. I may not know its value, but I know it just takes one value. And the random variable is what? It's multi-valued. So this variable can take multiple values. Each of them occur with certain probability. That's it. Right? This sentence you have to, this statement that I think I summarized this over the year. I think that's the best way for you to think about probability without going through all the equations. Otherwise, you'll be confused, okay? Again, random variable or random vector is multi-valued variable. It takes multiple values. It could be, all right? Could be 1, could be 2, could be 3. Each of these values occurs with certain probability, which we call probability mass function or probability density function. Okay, that's it. With that statement, then we can understand expectation, right? Expectation is that you gave me a random variable or vector. It does not take one value, it takes multiple values. If I want to use one number to represent it, is that it's a weighted sum, okay? It's all the value it takes multiplied by the probability that value occurs, and you sum them together, give you a weighted average of this variable or vector. That's expectation. Whenever you see expectation, the first thing you need to do is what? If you think about definition, expectation is nothing but a sum or integral. In this class, summation and integration are the same as well. Okay, you can think about them the same. That can help each other. Okay, these two formulas are exactly the same. Okay, mathematically they are equivalent and also the same. So it's a weighted sum of the values times the probability this value occurs. Once you think about them as a summation, then you can, because summation, you know how to sum two vectors. Do you? You know how to sum two vectors, right? Okay. So then you know how to compute the expectation. As simple as that. Okay. We can also say, some people, we can generalize. I don't require to do this. Let's say my x is n by m. It's a matrix, random variable. Can you imagine what it is? It's not a deterministic matrix, okay? It takes multiple values, and each value occurs with certain probability. And then you know how to compute expectation, right? Expectation is nothing but a weighted sum of those possible values this matrix may take. If you know how to do the summation of matrix, then you know how to do expectation of matrix random vectors or matrix random variables. Okay, I hope you can make this jump in your thought process. All right, so we discussed some properties, and then last time we are here about joint distributed random vectors. This is the most crucial part, okay? If we are dealing with random vector, it doesn't matter how many dimensions I have. I can put all of them, as I mentioned before. I can say x and y are jointly a big random vector, okay? I can fully specify this big random vector. But the reason we are studying these jointly distributed random vectors is because these two may have different meanings. I want to study these two relations. Okay, for example, the x could be Shenzhen's temperature. Okay, y could be Guangzhou's temperature. They are related. I don't want to put them as a two-dimensional vector because each of them has a special meaning. So that's why I want to study joint distribution. Okay, this is crucial. Okay, we know how to do the joint distribution is fully specified by the joint density function. What does this symbol mean here? So it is the probability, roughly, okay? It's density, it's not really a probability, it's a density. It's a probability x variable takes small x, y takes small y. X and y, capital X and y are random variables or vectors. They can take different values, right? And x takes small x and the capital Y equals small y. This has a probability, and that's the density, okay? Now let's talk about conditional density. That's the really important thing. I think you have learned all of this before. All of the formula appear here. I think you have learned or at least seen before. Did you? Yes? Do I need to explain? I may ask you, what's the meaning of this? So you may have seen this, right? Conditional density is like this. What's the meaning? How did you derive it? Did you show it, or you just memorize it for your exams in the probability class? We can derive it. How to think about this? This is a conditional density. It's still a density, yes. Conditional density, yes. He sees my logic. Conditional density by default is a density. Density of what? Of x or y or x and y? Which one? Conditional density is a density of x. Okay, this is the density of x. Okay, but I can also say this is called marginal, right? Marginal is also a density of x. What's the difference between this and this? This is, I don't know what y is, all right? I don't have any further information about the value y takes than the probability of x. Then this part is that I already know capital Y just equal to small y. After I know capital Y is small y, then is x still random? Of course. X is still random, right? And what does that mean by random? Multi-value. It still can take multiple values. Each of them occur with certain probability, right? So that's this is the density of the conditional x conditional on capital Y equal to small y. You can think about this. X is Shenzhen temperature. Okay, Y is Guangzhou. Okay? Or anywhere you want. I say Y equal to 26 degrees. But Shenzhen, you still don't know, right? It's still random. But once you know x, y is 26 degrees, you know Shenzhen will be close to that, right? Because we're really geographically close to Guangzhou, right? It gave me information that I didn't. But if I say this is 0 degree, it's really relevant. But that does give me, modify my belief about Shenzhen's temperature. But it's still random, right? It still has a density. Okay, this density is divided by this. Why we have this formula? This, you can think, I don't want to derive it. You can think of it as this conditional probability. Just follow from this conditional probability is what? Condition, an event of A, conditional B occurred, is A and B jointly occurred divided by probability of B. Okay, because B is the whole sampling space now, all right? This is that, Guangzhou is Y, that occurred. Okay, it's 26 degrees. Okay, so how do I modify my belief about X? Is they're joint, so capital X equals small x, capital Y equals small y divided by probability B. Okay, the same thing for, this may be easier to understand, for discrete cases. Okay, so probability A and B, given B is probability A and B divided by probability B. This is nothing but probability of B. This is equal to probability of Y equal to J, the B event, right? That's how you compute the marginal of Y by summing over all the possible cases for X values. I don't want to over-explain this. Somehow you need to make a link, connection in your mind between those formulas and this kind of conditional density and the conditional mass probability mass function. Okay, another important thing is the marginal can also be written like this. How do you interpret this? You should think about this as the law of total probability. This formula, I'm not sure whether you can see it. whether you can understand this, and this is nothing implies these density functions. You remember the law of total probability? You conditional on, let's say this is B1, B2, B3. Okay, if you want to compute the event, let's say this is my A. Okay, we will do this by divide and conquer. We intersect, we can do it. This is part of A1, A intersect with B1, some A intersect with B2, some A intersect with B3. And each of these by conditional probability formula can be written as conditional on B1 and times the probability of B1, etc. All right. If you like a pure mathematical derivation, that's also very simple. Is marginal of x equals probability. By definition, is joint dy, right? Is that true? That's marginal. You don't care what y is, so you integrate all the possible cases for y. That means summing all the possible cases for y for the joint density. Then because of this formula, okay, this one, let's call it 1. Because of 1, I will say this is nothing. You multiply this y here is y given y, x small x, times f margin of y and dy. Okay, that gives me this formula. That's very easy to derive, but I want you to understand. That's more important than derivation. Okay, and we all know independent formulas means independence, statistical independence means conditional on y values or not doesn't change the uncertainty of that variable. Then these two are independent. So independent, I think all of you remember this formula, right? The joint density function somehow can be factored, 分解, into multiplication of marginals. This is not the original definition for conditional probability. Original is what? I need to require this one is equal to this. Means y take whatever value doesn't modify my belief about x. This should be easy to understand, right? And then this one will imply this. Because of what? Because of this, right? Also because of 1. You multiply this y to the other side, then you plug in this, you get this joint factorization condition. Okay, so that's conceptual. I know it's if you understood it, it's very trivial. If you don't, it takes time. It takes exercise. We haven't gone through too much exercise yet. Now I'm going to start finally, okay, talking about conditional expectation. This is my definition. Xiaohan, can you explain this to me? This is a definition of conditional expectation. Can you explain this to me and to the rest of class in Chinese or English, whatever is fine. Try your best. You cannot say this is the formula. Do not read the formula. Just explain. Try to explain. Conditional expectation. Does this make sense to you, first of all? It's just an expectation. So it's like no need to explain, right? It's just a formula. Then my job will be easy. I will just read all these formulas, then we are done. Yuntian, can you explain?
I think it's the same as the expectation. When y have a certain value, then the distribution of x is affected. F, the PDF of x, the fx becomes of the conditional.
Okay.
So
Yeah.
this is a change.
You can teach now. Okay, good. Anyone disagree? That's, let me repeat, Yuntian's explanation. I think it's good, all right? Expectation, conditional expectation, conditional probability is probability. Conditional density is density. Conditional expectation is an expectation. What is expectation? Expectation. It's conditional expectation. It's like expectation of X, right? But the only thing that complicates our understanding is that I know Y is Y, all right? It's like a Guangzhou temperature is 26 degrees. I know this already. And conditional expectation is expectation. So it is the same as expectation, means it's still a weighted sum, okay? So given Y equal to small y, X is still random. Are you with me? Okay. Given capital Y equal to small y, X is still random. It takes multiple values. Each of them occur with certain probability. And I'm repeating this statement, right? And then expectation of this random X is just a weighted sum of all the possible values X may take, of course, given the condition Y equal to Y, right? And the likelihood each of this value occurs. You multiply this. This is the possible value X takes. This is the probability X takes this small x. Are you with me? Okay, it's just the possible value it takes times the likelihood that value occurs. Now, the only difference is what? The likelihood may change. Once you know Y equals 26 degrees, like let's know Guangzhou 26 degrees, then my belief about Shenzhen temperature may be modified. Okay, you need to use that modified density to compute expectation, but it's nothing but expectation. Okay, let's go to examples. I think that will help you. Let's try to read this table. What does this mean? It's that X and Y are jointly distributed, okay? X and Y are jointly distributed. This is a discrete random variables. The first question, what's the dimension of X? Xiaohan, what's the dimension of X? What about Y? One, okay? Y, it has 6. It takes 6 values. Each of them is a number. It's one dimension, okay? If this number is like 1, 2, like a vector, that will become 2-dimensional. You're with me? It takes multiple values. Each of them occur with certain probability. Okay, it's jointly distributed according to this table. Okay, now my question is the following. What's the expectation of X given Y equal to Y? Given Y equal to 1, given Y equal to 1, X is still random, right? So let's look at this. I prefer, maybe this may be confusing for some students, but let's write it like this. So Z equal to X given Y equal to 1. I'm not sure whether you can suffer from this ugly looking notation. What does this mean? I define this conditional variable as Z. So given Y equal to 1, X still random, it takes multiple values with certain probability, it's a random variable, okay? So I define this new random variable or conditional random variable as Z. That's fine, or I don't have to do this. I can just keep using this notation, but let's do this for now. Now let's look at Z is random or not. Yes, so what value Z may take? or x may take given y equal to 1. So y equal to 1, x can take 2, 3, 4. Maybe it's 5, 6, but there are 0 probabilities, okay? I can say z can take values like 2, 3, and 4. And the probability of this z is what? What's the probability of z equal to 2? Probability of z equal to 2 equals what? So the probability of zx equal to 2 given y equal to 1, okay? You have to understand this notation. So now I fix my word to, or constrain my word to the case of y equal to 1, okay? That particular case, x can still be random. I call that random variable z now. It's, how to compute this? It's the probability of x equal to 2, y equal to 1, divided by y equal to 1. Probability of y equal to 1. Okay? So what is it? Probability x equal to 2, y equal to 1 is this number. This is 1/4 divided by probability y equal to 1. What's the probability of y equal to 1? It's summation of these cases, right? Because y equal to 1, I don't care x. So x can be 2, 3, 4, either way is fine. They all contribute to the case of y equal to 1, so I need to sum them together. This is the formula of marginals, right? This y, well, yes, y equal to 1, I need to integrate out x, sum over all the possible x. So that will be divided by 1/4 plus 1/8 plus 1/8. Overall, it's, what is it? This is half, right? 1/2 divided by this will be still 1/2, right? This is 1/2. So this is 1/2. Okay, we can continue. What's the probability of z equal to 3 or x equal to 3 given y equal to 1? It's just half of this, right? Okay, 1/4. Okay, this guy is the same, 1/4. Do they sum up to 1? Yes, of course. Because conditional probability is probability. All the cases have to sum to 1. Okay, now we find out, given y equal to 1, x still take 2, 3, 4. Okay, this is nothing but, this is the same as x given y equal to 1, right? So now if I want to say conditional expectation of given y equal to 1, expectation of z is, these are shorthand notation. Z is shorthand notation of this only. You can think about this as a new random variable with different domains and different probability. That is what? The expectation, right? Now we are computing expectation. Xiaohan, I ask you to define it again. Can you tell me how to compute this? Okay, times this, yes. All right, good. What is that? Nothing. What? The value it takes times the likelihood its value occurs is the expectation. Conditional expectation is just we modify the likelihood of its value now. Because after I know some event occurred, then those probability of the other random variable becomes changed, right? Got changed. This will be, I think it's 11 divided by 4. Okay, that's a number. Now we know how to compute conditional expectation. So we're ready to do Kalman filter? Not really, okay? This is the simplest case. You have to exercise quite a bit. And you can try, that's yours, okay? Verify yourself or do it your own. Okay, I would say this is a similar, I wouldn't repeat them. This is similar approach. You can get these numbers. How to compute them? First of all, let me try to ask. Still the same. You first need to know, given y equal to 2, x is still random. Okay, you think, following my statement, okay, think like if you are thinking with me, okay, given y equal to 2, how to decode this kind of symbol, okay, given y equal to 2, x is still random, okay, take multiple values, each of them has certain probability, then I just need to do weighted sum, okay, so repetition of this particular argument will help you go through conceptually hard things. Now it's still easy. Once it gets hard, it will help you quite a bit. Okay, now let's look at a continuous case. Example 2, suppose x, y is uniformly distributed on the square as, this is a square, let me draw it. So x and y, each of them is, let's say this is 6, this is 6, negative 6, positive negative 6, this is 6, negative 6. So there's a square uniformly distributed in the square. Sorry, that's, we should have this pass through this. So that's my, all the possible values x and y can jointly take. So now given this uniformly distributed on the square, what does this mean? So each value, each number in this area is the same, has same probability or same likelihood to occur, right? So does this tell you the density? From this statement we know the joint distribution of x and y equal to what? It's continuous, you have a density function, right? So 1 over, this is 12 by 12, it's the area, right? So it's 1 over 144. If x and y, these two values belong to the square, okay? It will be 0. It will be 0. It will be 0. Let's see. Where is it? It will be 0 otherwise. Can you understand this part? So it only occurs in this square, but why we have this? Assume6不属于什么？都无所谓啊，没有渠道啊。It's continuous。可以，在 continuous 里边一个 number 是无所谓的，你可以这样。什么？小于6可以无限接近6吗？144什么？对啊，是不会变的。Okay. Because it's uniform, that means it's a constant within the square. If you integrate out this constant, c, within the square, dx dy, it has to be 1. So this constant will become this. All right, that's how I got this. Because uniform distribution, that means it's the same number. Okay? All right, now let's, I don't want to, let's erase this part. So we need to compute. Now, this question, we need to compute. I want you to find conditional expectation of y given x. So we need to compute this. So, so that's y given capital X equal to small x. Okay, Xiaohang, can you explain this to me? Given x, you have to follow my statement, okay? Expectation of y given x equal to small x. What is it? Okay. Okay. When you see expectation, no matter if it's conditional or not, it's an integration or summation, right? Integrate the sum. Okay, let's think about it as if we are engineer. We are, right? Because we are engineer, we can think that way. Okay. It's the value this y may take times the likelihood this value occurs. So that will be probability of y now given x, this y equal to small y given x equal to small x, d of what? dx or dy? dy, because it's sum over all the possible value of y takes, right? So I can say this from y is, I know it's a scalar, it's from negative infinity to positive infinity. If they go over this 6, that's fine, it's 0, right? You integrate something 0, it's fine. So, but in the most general formula, you should be able to write it down like this, right? So to do this integration, what you need to find? You need to find the conditional density. That's it. Then become calculus, not my job anymore. This is not my job either, okay? So, but I have to review this for you. How to compute this? Y given x, y given x, all right? So that's by formula is joint divided by marginal of x, okay? Probability A intercept B divided by probability of B. That's like that, right? So first of all, we need to find all of this. So first of all, what is the margin of x? Integrate out y, right? You don't care about y, so that will be divided by y. So the joint, you integrate over y, you get the marginal of x. What do you think this function is? You should be careful, okay? X can take value arbitrarily, right? But outside 6, this box region, it will be 0. Because this guy only has value in S, all right? So if X is already outside this box, then it's 0, right? So this will be 0 if X does not belong to negative 6 to 6. Are you fine with this? Of course, right? If the outside is 0, because the density is 0 outside. Okay. But some people can direct write down the formula, but I want you to go through the baby steps so that you know, as if you are a programmer, how you should derive the things. Okay. Now the question is that if this guy is inside this, what is the integration? So I don't care about y, right? So y can be arbitrary. So, but the most, from negative infinity to infinity is also fine. But the only thing it has value is from negative 6 to 6, 1 divided by 44 dy. Okay? So this guy is this guy in this domain. Outside this domain is 0, so you don't need to integrate that. So overall, I will have margin of x is, let me swap the order. So the 1/12 if x belongs to -6 to 6 and 0 otherwise. It's also uniform in this particular case. Okay. The next question I need to ask is y given y, small y x. Yes, y given x, small y and small x. That is, it's just you know this function and you know this function, you just divide them, right? But you need to make sure you discuss all the possible cases, because this function is defined in terms of its domain. It has different expression. Okay. So here it is 1/144. Suppose, okay, if x and y belong to the square, okay, then the joint is 1/136, and the marginal is 1/12. So it's 1/12 if it's in the square. Otherwise, what is it? If the outside square is 0, okay, it won't have any probability. It's not possible. Okay, so this tells me conditional expectation of y given small capital Y equal to small x equal to y given x, small y given x dy is integrate from -infinity to infinity or -6 to 6, right? So it only has values when y is from -6 to 6, but it's symmetric, so it's 0. Okay. So conditional on x equal to small x. So if I tell you, okay, I know x is here, then y can still be random, right? Around here, it's only this line, and it's still uniform, so the expectation is 0. Okay, if from the figure you can see it right away, but I want you to follow the steps to have the correct calculation. Okay. Suppose this is my small x. Any questions? Then we can take a break.